Alright, so today we're going to be going over some Lewis structure examples for some molecules and molecular ions, and hopefully by this point you've already watched the Lewis structure and molecular structure videos. Otherwise what we're going to be doing here is not really going to make much sense. So in this video we'll be doing some more complicated examples than what we were doing in the previous videos. So first up we have here phosphorus pentachloride. So this is going to be PCl5. And in this, we of course always count our valence electrons out first. So here I have 1, 2, 3, 4, 5 for my phosphorus, and then that's going to be 7 for my chlorine. And that's just going to work out to be 40 valence electrons. So we of course just start by putting the phosphorus, because always my first atom here is going to be the central one, then the rest are going to just go on the outside. And then we just put bonds between each of the phosphorus and the chlorines. And just remember each bond represents 2 electrons. And then we just put the rest of the electrons on the chlorines. So I have here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40. And I don't have any electrons left over, so I don't have to put anything on my central phosphorus. And then as for the orbital hybridization of my central atom here, well, here this is going to be attached to 5 things, and there's no lone pairs on there. So that means for my phosphorus, and always for the hybridization, we're just going to worry about the central atom. We're not going to worry about the outer atoms. We could do that as well, but for our purposes, we'll just worry about the central atom. So this is attached to 5 things. So this is going to be an sp3d, because of course there's one s plus 3 p's plus a d. It's 1 plus 3 plus 1, that's 5. There's 5 things attached here. And then as for our structure, it's going to be right here, the trigonal bipyramidal. So we're going to have, in the structure here, the chlorines on the top and the bottom, and then these other chlorines basically around the equator, separated by 120 degrees like this. So that would be, our molecule like that. Next up, we're going to have the sulfur tetrafluoride. Once again, our valence electrons. So sulfur is going to have 6 valence electrons, and then my fluorine is going to have 7. It's going to be 34 valence electrons for that one. So just put my sulfur in the middle and stick my fluorines on there and put my bonds. So I have here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. And I have 2 more left over. That's 33, 34. So my sulfur there has a lone pair of electrons. And then we just go here and calculate our formal charges, and I should have done that over here actually. I'll just finish this one up. So we calculate our formal charges. So the formal charge on the fluorine is going to be, there's 7 valence electrons minus, I have 1 line and 6 dots. So that's going to be 0. And the formal charge on my sulfur, that has a valence of 6 minus 4 lines plus, and you can see here 2 dots, so that's equals 0. So that's 0, so that's perfectly fine over there. And then as for my hybridization on this, this has 1, 2, 3, 4, 5 things there. So this is also going to be that sp3d. And in this case, it's going to be that sawhorse or the seesaw configuration here. So we're going to have the 2 fluorines up on this way, and then these 2 fluorines over here with the electron pair kind of shooting out. Okay, so this is going to be the seesaw. Oh, and just going back to this one because I forgot to calculate my formal charges. The formal charge on my chlorine, that's just going to be 7 valence electrons for each chlorine minus the 1 line and 6 dots, which is 0. And the formal charge on my phosphorus, so of course that has the 5 valence electrons minus the 1, 2, 3, 4, 5 lines and 0 dots, so that's 0. That adds up to 0, and we're good with that one. And like we said before, this one here is going to be that trigonal bipyramidal. Okay. And next up we're going to be looking at some oxyanions here. So here of course is the hypochlorite, which is our ClO minus of course. So the valence electrons in this, so we're going to be seeing this quite a bit, but of course the chlorine has the 7, the oxygen has the 6, and we of course have to remember our extra valence electron there because it's a negative charge. That's going to be 7 plus 6 plus 1, it's going to be 14. So Cl and an O. Obviously can't get more simple than that. And we're just going to put our 14 electrons. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. All right, and then as for my formal charge on this, so the formal charge on my chlorine, it's going to be 7 minus 1 line and 6 dots. That's 0. And on my oxygen, that's going to be 6 for my valence electrons minus the 1 line and 6 dots. That's going to be a negative 1. Of course, this adds up to negative 1, which is good because that's the charge in my ion. And as for this thing, it's basically just going to have a slight little negative charge up here, which is fine. And also remember that the oxygen, in this case, is more electronegative than the chlorine, so we'd want the negative charge on the oxygen. So, yeah, that's just going to be my Lewis structure for that. And as for the hybridization on my central atom here, well, my chlorine, as you can see here, it's basically, it has one bond, and then it has 1, 2, 3 extra lone pairs around it. And then as for it, well, it would obviously just be a linear molecule. And, well, it's technically not actually on this sheet there, but you would basically have, an sp3 because it's 1, 2, 3, 4 things on there. So it would be an sp3, but it would be linear. But I won't give you any kind of tricky ones like that because it's a little bit odd. So sp3, and again, this would be a linear one because it has 3 unpaired electrons around the outside. All right, the next one is just chlorite. So that's going to be ClO2 minus. So in this case, my valence electrons, 7 for the chlorine, plus 6 times 2 for the oxygens, plus another 1 for the negative charge. That's going to be 20 valence electrons on there. So again, chlorine in the middle, and then the oxygens on the outside. And this is going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. And then we figure out our formal charges. So on the chlorine, this is going to be 7 minus 2 lines and 4 dots. That's going to be a positive 1. And the formal charge on each oxygen is going to be the same. It's going to be 6 minus 1 line and 6 dots, minus 1. And of course I have 2 of these, so that's going to work out to be a minus 1. So in this case, of course, we want to minimize my formal charge of my chlorine. So we're basically just going to move one of these little electron pairs over to get a double bond onto the chlorine like so. So we would have here my chlorine, single bond to the oxygen, double bonded to that one. And then we would have here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. We can just double check our formal charges. So this is for the double bonded oxygen. That's 6 minus, and again, 2 lines, 4 dots, 0. Formal charge on the chlorine, that's going to be 7 minus 3 lines and 4 dots. And then for my oxygen over here, that's going to be exactly the same. And then right here, this is just going to be the formal charge here for my atoms. So my oxygen, in this case, is going to have the slight negative charge like that. And actually, in this case, there would be a resonance going on because I really can't say, why did I move this one and not this one? So I could very easily just go here, the oxygen, like that. So basically, there would be a resonance kind of structure going on with this. As for my chlorine, what is its hybridization? What is the shape of this ion? Well, here, the chlorine here has 1, 2 things it's attached to, plus 2 more lone pairs. So this is going to be an sp3 hybridization. There's 1, 2, 3, 4. And then as for its shape, well, attached to 2 things with 2 lone pairs, this is going to be the bent or angular configuration. So this is going to look like a water molecule, shape-wise. All right, next up we have the chlorate. That's ClO3 minus. So once again, our valence electrons, 7 for the chlorine, and then 3 times the 6 for the oxygens, plus another 1. That's going to be 26 valence electrons. So once again, chlorine in the middle, and then the oxygens on the outside. Draw my bonds. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. Okay, check my formal charges. So on the oxygens, and we've seen this a bunch of times. So for my oxygens here, that's going to be 1 line and 6 dots. That's going to be a minus 1. The formal charge for my chlorines, and of course there's 3 of these. That's 7 minus, and now there are 3 lines and 2 dots. And that's going to be a plus 2. Now it's going to be negative 3 plus 2. That's a minus 1 formal charge. So obviously we can make this a little bit better. Now chlorine, of course, can accommodate more bonds and everything on there, so we can actually move several of these up here. So basically what I can do is just move 2 of these lone pairs up to make double bonds, and I'll wind up here with singly bonded oxygen, chlorine, double bond, like this. And then we just have to put our electrons around. So I have here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. And then we can just figure out our formal charges for this one. Now, I want to put the formal charges over here just so we... So the formal charges for this, for my oxygen, I put this here for my singly bonded oxygen, which I have. So that's just going to be exactly what we had here before. Formal charge for my doubly bonded oxygens. Well, that's going to, we've seen this before already. 6 minus, and now there are 2 lines and 4 dots. And the formal charge on my chlorine. So that's going to be 7 minus 1, 2, 3, 4, 5 lines and 2 dots. Of course, that adds up to -1, which it should be. Now, the reason I wrote this up here is because actually there's going to be resonance structures for this. You can write this as the resonance, like so. Now, as for the shape of these ions, notice here the chlorine is attached above. We saw here that was an sp3 because, again, this one was attached to, well, 2 things and 2 lone pairs. Well, this thing is now attached to 3 things and 1 lone pair. So this is still going to be an sp3 hybrid, and this is going to look like the ammonia molecule, 3 things and 1 lone pair on it. So this is going to be a trigonal pyramidal shape. All right, and then finishing out all the chlorine oxyanions right here, we have the perchlorate, ClO4-. All right, so my valence electrons, 7 like we've seen, plus 4 times 6, plus the extra 1 in there, and this is going to work out to be 32 valence electrons. All right, so once again, we just start here with the chlorine in the middle, and stick my 4 oxygens on the outside. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. All right, so we actually don't have any lone pairs on my central chlorine atom this time. And then we, again, check our formal charges. It's going to be 6 minus 1 line and 6 dots. It's -1. And again, I have 4 of these for that. And then the formal charge on my chlorine, 7 minus, and now there are 4 lines and no dots. So it's going to be a +3. So -4 plus 3, that's of course -1, which is good. And again, we just want to make sure this gets as close to 0 as possible. So we're just going to take these, move them over, 1 of these over, 1 of these over, and what we wind up with here is the oxygen, Cl double bonded to a whole bunch of oxygens. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. And there will also be the appropriate hybrids for this as well, with the appropriate little electron dots. I just don't feel like putting them all in. And then, of course, we can just double check our formal charges. It should be kind of obvious, it should work out by now, but just to go to good practice. So for my single bonded oxygen, we've seen this a bunch of times before. And for my chlorine, there's 1, 2, 3, 4, 5, 6, 7, and no dots. So that's 0. Add that up, and again, that's -1, like your charge should be. And then as for my hybridization and the shape of this, well, here there's attached to 4 things. There's no lone pairs. So this is going to be an sp3 hybridization. This is going to be my nice little tetrahedral shape, just like the methane molecule. All right, most of the time I'm not going to ask you to actually write out all the resonance structures here. Just know that there's resonances going on, and they're all basically equivalent. You just take the average of these 4 structures to figure out how your actual molecule does look. And the thing is, we've seen we have here like perchlorate, perbromate, periodate, and all the other oxyanions go with the chlorine, the bromine, the iodine. We've seen those. But we're never going to see anything with the fluorine because fluorine, doesn't have these extra orbitals and everything to basically accommodate it. So that's why you're never going to see basically like, FO4-. It won't exist because you can't access any additional orbitals you would need for that. All right, for our next one, let's look at carbonate. That's CO3 2-. So my valence electrons, there is going to be 4 for my carbon. Right, that's 1, 2, 3, 4 for my carbon, of course 6 for each of the oxygens. And then 2 more for my charge. So of course that's just going to be 24 valence electrons. So we just start here, putting my carbon in the middle and sticking my oxygens around the outside and putting a single bond. So that's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. All right, and then we just go here and calculate my formal charges for all of these. So for my oxygen, we've seen this a bunch of times. So 1 line and 6 dots. And of course I have 3 equivalent oxygens. And then for my carbon, in this case that's going to be 4 minus, because that's my valence electrons, minus 3 lines and no dots. So this is just going to be a +1. So that's going to be -3 plus 1, that's a -2, which of course is my charge in the ion. So what we're going to do is just move one of these little bonds over to here, and we're going to wind up with the oxygen single, like so. Whoops. So that's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. You know, this is again is going to undergo the resonance structures. All right, and then I can just, it's kind of obvious. You remember we've seen this double bonded thing here for the oxygen before. And then for my carbon, that's just going to be 4 valence electrons minus 4 lines and no dots. That's obviously 0. So these are going to be, basically my -1 charges are going to be out here. Okay, so basically this is usually the way that your carbonate would basically kind of be written like that. So that's your 2 negative charges on your oxygens. And again, oxygen is going to be more electronegative than the carbon, so your negative charge would want to be there. And if you were dealing with something like bicarbonate, by the way, well, in this case, if you had your bicarbonate, well, this would just look like this. So that would be your bicarbonate. And then if you were to make carbonic acid, and by the way, bicarbonate, as everyone should hopefully know, is HCO3 minus, and then carbonic acid would be very easy, just like that. And by the way, since we forgot this, the hybridization, of course, on my carbonate, well, notice it's attached to 3 things, and there's no lone pairs. So this is going to be over here, the trigonal planar one, and this is, of course, going to be sp2. All right, as for the next one, let's look at the iodine trifluoride. So this is IF3. So we have 3 halogens basically bound to each other. So my valence electrons here, it's going to be 7 for my iodine plus 7 times 3 for my fluorines. That's just going to be 28 valence electrons, because of course fluorine and iodine are both halogens. So central atom, of course, is going to be my iodine. And then I'm just going to stick 3 fluorines around there. And bonds. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28. I'll just check my formal charge. So on the fluorine, there is going to be 7 valence electrons minus 1 line and 6 dots, 0. And the formal charge on my iodine, again, 7 valence electrons. Then I have your 3 lines and 4 dots, which is 0. That adds up to be 0. And yeah, we're good with our structure, so we don't need to move electrons around, so that's nice. As for my hybridization, notice right here I have 1, 2, 3, 4, 5 things that it's attached to. So this is going to be an sp3d hybridization. And as for the shape, this is going to be that T-shaped. So you're going to have your 2 lone pairs out here, and then basically the fluorines are going to be arranged 90 degrees relative to one another. So that's going to be the T-shape. All right, next one, we're going to add 2 more fluorines onto this. So this is going to be iodine pentafluoride. So IF5 in this case. So the valence electrons, 7 for the iodine, and now 7 times 5 for my fluorines. And that's just going to work out to be 42 valence electrons. So we, again, just put our iodine in the middle, stick our fluorines around the outside, and put the bonds on. So that's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40. Got 2 left over. So these go on the iodine like so. And we just check our formal charges. So for the iodine, this is going to be 7 minus, now there's 1, 2, 3, 4, 5 lines and 2 dots. That's going to be 0. And for each of the fluorines, which are all equivalents, 7 minus, again, my 6 lines and 1 dot, or 6 1 line and 6 dots, which works out to be 0, so we don't have to move my electrons around at all, so that's nice. And then as for my hybridization, well, it's attached to 5 things in an electron pair, so that's going to be 6 things total, so this is going to be sp3d2, like so. And then as for the shape, this right here is going to be my square pyramidal. So we're going to have my 4 fluorines around here, basically around the equator, arranged in a square with another fluorine sticking up top. All right, next up we're going to look at xenon difluoride. All right, so this is going to be XeF2. Now, xenon, of course, is a noble gas, and usually you would say, well, noble gases don't form any compounds, but it turns out that fluorine is so reactive, and the xenon has a fairly low ionization energy that it can actually form some chemical compounds with fluorine and oxygen as well. We'll be looking at a couple of these. So the xenon difluoride, so the valence electrons we have, so xenon is a noble gas, so it has 8 valence electrons, and then the 7 times 2 for the 2 fluorines. So this is going to be 22 valence electrons. So here's my xenon, here's a fluorine, there's another fluorine. It's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. So the xenon here has actually 3 lone pairs of electrons. And here we can just double check my formal charges. So for the xenon, it's going to be 8 minus, I have 2 lines, and 1, 2, 3, 4, 5, 6 dots. So that's going to be 0. And the formal charge in my fluorines, 7 valence electrons minus a line and 6 dots, which is going to be 0, and that's just adds up to 0 even though I have 2 of them. So I don't have to move any electrons around, it's all single bonds. My hybridization, this is attached to 2 things and 3 lone pairs, so that's going to be an sp3d, because that has 1, 2, 3, 4, 5. There's 5 things there, right? 1 s, 3 p's, and a d. And as for my shape, well, this is obviously going to be linear. Right, so that's obviously linear. And we can see right here, this is going to be this shape right here. So there's my sp3, there's my 3 lone pairs around the equator, and my 2 fluorines would be above and below, separated by 180 degrees. All right, next up we can look at the xenon tetrafluoride. So in this case, we're going to have my valence electrons, so 8 for my xenons plus 7 times 4 for my fluorines, and that's going to be 36 valence electrons. So once again, my xenon in the middle, and my 4 fluorines are on the outside. So my bonds, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, and I need 36. So it's only 33, 34, 35, 36, like so. All right, so there's going to be 2 lone pairs on the central xenon atom. Check my formal charges again. So on my xenon, 8 valence electrons, minus 1, 2, 3, 4 bonds, and 4 dots. That's 0. And then for my fluorines, we've seen this a bunch of times, so it's going to be 7 minus 1 line and 6 dots. So that's 0. So this all adds up to 0, so we're good. As for the hybridization of the molecule, well, it's attached to 4 things, 2 lone pairs, so that's 6 things total. This is going to be an sp3d2. And the shape for this, you can see, is going to be the square planar. So I'm going to have the 4 fluorines arranged around the equator with the lone pairs above and below there. All right, next up we have a molecule called xenon oxytetrafluoride. All right, now this one is not a binary molecular compound that we've dealt with before. Obviously I wouldn't expect you to be able to get the formula just by the name here, but it's actually going to be XeOF4, like this. So it's a xenon in the center again with the oxygen and the fluorines arranged around the outside. So basically our valence electrons again, there's going to be 8 from the xenon plus 6 from the oxygens plus 7 times 4 for my fluorines. So this is going to be 42 valence electrons in that case. So I have here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, and then another 2, 41, 42 on my central xenon atom. All right, so the formal charge on my xenon, that's going to be 8 valence electrons minus, I have here 1, 2, 3, 4, 5 lines and 2 dots, and that's going to be a +1. The formal charge on my oxygen 6 minus, and here I have 1 line and 6 dots again. It's going to be a -1. And the formal charge in my fluorines, 7 minus, and again 6 lines and a dot, or 1 line and 6 dots. That's going to be 0. So that's up to 0, but obviously we see here we have a +1, -1 difference. So we're going to need to move my little electrons around here to make a double bond. So we'll wind up here with an oxygen double bonded like so to my xenon, and my fluorines out like this. And then we can just put our electrons around. So that's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, and double check all of our formal charges. So in this case, that's going to be 8, and now I have here 1, 2, 3, 4, 5, 6 lines plus 2 dots. So that's going to work out to be 0 for my oxygen, and the fluorine's exactly the same. So that obviously just works out to be 0. As for my hybridization, in this case, well, here I'm attached to 1, 2, 3, 4, 5 things in a lone pair, so that's going to be 6 things total. So this is going to be an sp3d2. And as for my shape, this is going to be the square pyramidal. So I'm going to have the 4 fluorines arranged on the equator in the square configuration, and then my oxygen sitting up top over here. So this is going to be square pyramidal. All right, next up, we're going to look at the phosphate. That's PO4 minus. So my valence electrons again. Remember phosphorus, that's 1, 2, 3, 4, 5 for my phosphorus, 6 for my oxygen. And then another 3 here because of my negative charge, 32 valence electrons. So here's my phosphorus with the oxygens all around it. 1, 2, 3, 4, 5, 6, 7, 8. And then the rest of my electrons, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. Check my formal charges. So on my oxygens, it's going to be 6 minus, and again, we've seen this a bunch of times, 1 line and 6 dots, -1. And the formal charge on my phosphorus will be 5 minus another 4 lines and no dots, +1. Of course, there are 4 equivalent oxygens. So it's going to be a -4 plus 1. So that's going to be a -3, which is our charge, so that we're good. But of course, we want to try to minimize this down, so we're just going to take one of my lone pairs here, move it so I can make a double bond like this. And eventually what we'll get here is that my phosphorus double bonded to an oxygen, single bonded to my other oxygens like so, with the electrons around. And once all this is done, again, you can just double check, but essentially what you'll find here is that all my oxygens are going to be -1 like so. And then that's going to be 0, that's going to be 0, because obviously for my phosphorus, that's going to be 5, minus 1, 2, 3, 4, 5 lines, no dots, so that's going to be 0, so that's going to work out very nicely. As for my hybridization for this, it's attached to 4 things, no free electron pairs, so this is going to be an sp3 hybrid. And then as for my shape, that's just going to be my little tetrahedral thing like before. If we were to look here at what phosphoric acid looks like, and of course there's actually resonance structures, I don't feel like writing all of them out, but essentially you can just write it like this. And then as for what my phosphoric acid would look like, well, here would be my phosphorus double bonded to an oxygen, then single bonded to an oxygen and a hydrogen, and then just put the lone pairs around there. And of course that would be phosphoric acid. Okay, next up we can look at sulfate. So that's, of course, SO4, 2-. Well, sulfur has 6 valence electrons, plus 6 times 4 for my oxygens, plus another 2 over here for my charge. So that's going to be 32 valence electrons. And then we simply start out like we always do, sulfur in the middle, and then oxygens around the outside. So that's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. Check all of my formal charges. So on my oxygens, it's going to be 6 valence electrons minus my 1 line and 6 dots. It's going to be -1. Formal charge on my sulfur, again 6 valence electrons, and now 4 lines and no dots. And of course there are 4 equivalent oxygens up here. That's going to be a -4 plus 2. It's going to be a -2 charge on that. So what I'm going to do here is just move my valence electrons over to make double bonds. And we're going to wind up here with the oxygen double bonded to a sulfur, double bonded to an oxygen, with 2 oxygens on the outside like this. So this is going to have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. Right, and then we just go here and double check our formal charges. So on the doubly bonded oxygens, this is going to be 6 minus, and now there are, and of course here we have 2 lines and 4 dots. That's going to be 0. Formal charge on my singly bonded oxygens, same thing as up here. And the formal charge on my sulfurs, 6 valence electrons, and now there's 1, 2, 3, 4, 5, 6, and no dots. And of course there are 2 of these, also 2 of these, not that it matters, and you wind up with a -2 charge. So these 2 little oxygens on the end would have the -1 charge. There is also resonance structures going on, but I don't feel like writing all that out. So this is going to be your Lewis structure here for the sulfate. And of course, if you were to make this into sulfuric acid, it would look like this. That's H2SO4. And of course, before we forget, my hybridization on this, it's attached to 4 things, no lone pairs. So that means that this is going to be, an sp3 hybrid. And like we saw before, that's just going to be your tetrahedral configuration. All right, next up, we're going to look at the sulfite anion. That's SO3 2 minus. Okay, so we'll see how this looks compared to my sulfate, which we just did. So again, my valence electrons, 6 for my sulfur, and now 6 times 3 for my oxygens, plus the 2 for the charge. So that's going to be 26 valence electrons. So here's going to be my sulfur and the oxygens around there. So that's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, and 2 more, 25, 26, like so. Check my formal charges. So for each of the oxygens here, and we've seen this many times, and there are of course 3 of these, and the formal charge on my sulfur, that's 6 minus, and now there's 3 lines and 2 dots. So that's going to be a -3 plus 1, -2 total formal charge, which is fine because that's my total charge there. So that means we're going to go here and move one of these over. And again, there's going to be resonance structures, so we're not going to worry about them here. It's going to be the sulfur, oxygen, oxygen, double bond like that. So there's going to be my sulfate, and the negative charges are going to be out here. And just for kicks, we'll just verify our formal charges. So for my double bonded oxygen, 6 minus, and now there's of course 2 lines, 4 dots. My singly bonded oxygens, which is exactly the same from above, and we have 2 of these. And the formal charge on my sulfur, this is going to be again 6 valence electrons minus 1, 2, 3, 4 lines, and 2 dots. So that's going to be 0, -2 charge on that. So of course this is just going to be my sulfite. And as for my hybridization, this is going to be an sp3 because it's attached to 3 things in 1 lone pair. And just like over here, 3 things, 1 lone pair, that's going to be my trigonal pyramidal, so it'll look like the ammonia molecule. All right, and just like with the sulfuric acid above, if we were to make sulfurous acid, in this case, the hydrogens would just attach to these 2 little oxygens right on the end. Now we can also look here at sulfur trioxide. So this is SO3. Okay, before we just saw sulfite, SO3 2 minus, this is sulfur trioxide, just the SO3. So again, that little charge will make a big difference in how the molecule is actually put together. So my valence electrons, 6 for my sulfur, plus 6 times 3 for my oxygens. And this, of course, is going to have 2 less than before, so it's only going to be 24 valence electrons. So here is going to be my sulfur with the oxygens around it. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, like so. And then we can just check our formal charges. So for my oxygen, it's going to be 6 minus 1 line and 6 dots. That's going to be a -1. And of course we have here 3 equivalent ones. I'll multiply that by 3. So the formal charge on my sulfur, 6 minus, and now there's only have 3 lines and no dots. That's going to be a +3. That's -3 plus 3. That works out to be 0. So what we're going to do in this case is take these lone pairs, move them in, like so. So now we're going to have double bonds with all of my oxygens. So we're going to have here sulfur, double bonded to this oxygen, double bonded to that oxygen, double bonded to this oxygen. And now we have here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. And the formal charge on my doubly bonded oxygens now. So this, of course, is going to be 6 minus 2 lines and 4 dots, which is 0. And on my sulfur, 6 minus, and now there's 1, 2, 3, 4, 5, 6 lines and no dots. So that's going to be 0 in that case. So you can see the difference here between the sulfur trioxide, where we had these lone pairs on there, and we end up with a resonance structure between a single and double bonds and all that, and this one where we just have double bonds all the way around. As for my hybridization, well, it's attached to 3 things, no lone pairs. This is going to be an sp2 hybridization, and as we see over here, that's going to wind up to be trigonal planar. Alright, next up we're going to look at azide, or azide, depends on how you pronounce it. So the azide anion, right, this is one you may have seen around. It's N3-, and sodium azide is actually what they use in airbags. So when this is triggered by electrical pulse, the sodium azide breaks down to nitrogen gas, and that is what lets the airbag expand very, very fast, in a couple of milliseconds. So this is a highly unstable compound that they use in airbags. So as for this, this is actually just going to again be basically in a line that we're going to do this. We're going to figure out if this is bent or not when we do our Lewis structure. So first up, the valence electrons. Well, there are going to be 3 times the 5 for the nitrogen plus another 1 for the -1 charge. That's going to work out to be 16 valence electrons. So it's going to be a nitrogen, nitrogen, and a nitrogen. So we'll just put our electrons around there. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. All right, check my formal charges. So I'm just going to label this nitrogen 1 and nitrogen 2 so we keep these straight. So the formal charge on my nitrogen 1 here, it's going to be 5 minus 1 line and 6 dots. So that's going to be -2. And then the formal charge on my nitrogen 2, which is my central one, it's 5 minus, and in this case there's 2 lines and no dots, so that's going to be a +3. And of course I have over here 2 of these equivalent ones, because I have one on the end and then one on the other end here, so it's going to be a -4 + 3, so this is going to wind up to be a -1, which we want. Alright, so as for trying to minimize this, well, what we could do is, move 2 of these over here and we could get this down to 0, but then we'd still have a -2 over here. Or we can basically just kind of like split the difference and move one of them over from this side, one of them over from this side, and that'll probably work out to be best in this case. So we'll basically move like one of these over here and one of these over here, and then see what we actually wind up with. So I have the nitrogen here, double bonded to this nitrogen, double bonded to that nitrogen. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So in this case, the formal charge on my nitrogen 1, so that's that same one there, 5 minus, and now I have here 2 lines and 4 dots. So that's going to be 6, 5 minus 6, that's going to be a -1. The formal charge on my nitrogen 2 is 5 minus, and now there's 4 lines and no dots, +1. And again, I have up here times 2 of these, so that's still a -1 charge. Now, I can't really move any more around to make this any better, because remember, my nitrogen can only take a total of 8 electrons, because it's in this top row, so there's no expanded octets or anything for these atoms over here. So because of this, this is basically as good as I can do. My formal charges are never going to get to 0. It's just simply not possible, but this is what my molecular anion will look like. So I'll basically have here a slight negative charge here, a slight positive charge here, and a slight negative charge over there. And that's just the way it works. All right, as for my shape, so right here, this is going to be attached to 2 things, no lone pairs. So this is going to wind up, just like the carbon dioxide, to be linear, and that's going to be an sp configuration. Here we have the I3-, which is triiodide. So this was the azide N3-, this is I3- over here. So you might think they're going to be similar, but they're going to be a little bit different. So my valence electrons in this case, that's going to be 7 times 3 because they're all halogens, plus another one, so that's going to be 22 valence electrons. So here's going to be my iodine on either side, like so. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. Big difference here because we're now dealing with the halogen. So check my formal charges on each of these. So this is going to be I1. This is going to be number 1. That's going to be number 2. So this is going to work out to be 7 minus, and now there's 1 line and 6 dots. That's going to be a 0. And the formal charge on the iodine 2, 7 minus, and now I have 2 lines, and 1, 2, 3, 4, 5, 6. So that's going to be a -1 charge. So that works out to be a -1 like so. All right, and at this point, of course, there's 2 up here, so it doesn't really matter. And there's no way to really move this stuff around to move my negative charges, so this is what we'll have. So essentially, there'll just be a slight little negative charge here on the central one. As for my hybridization, well, this is attached to 2 things plus 3 electron pairs, so that's going to be 5 things total. So this is going to be an sp3d hybrid, and the shape of this is going to be linear. So right here, this is the sp3d hybrid, attached to 2 atoms and 3 lone pairs around here. So there's my 2 atoms, 3 lone pairs. So this is obviously just going to be linear. So you can see basically between the azide, which is sp and linear, and the triiodide, this is sp3d and linear, just like that. All right, and then one last one, the final chloride. So this is SOCl2. All right, so this is sulfur in the middle with an oxygen and 2 chlorines on the outside. So here, this is going to be a, well, first of all, my valence electrons. So it's going to be 6 for my sulfur, plus 6 for the oxygen, plus 7 times 2 for each of the chlorines. So that's going to be 26 valence electrons. So there's my sulfur, an oxygen, and a chlorine, and a chlorine. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, like that. My formal charges on my oxygen, 6 minus, and again, 1 line and 6 dots. On my sulfur, 6 minus, and there's 3 lines and 2 dots. And the formal charge on my chlorines, each of them, and there's 1 line and 6 dots. Add that up, and that's going to be 0. And of course I have 2 chlorines, not that it really matters. So I would just want to make these closer to 0. So what I'm going to do here is just move these lone pair over to make a double bond. So I'll have here the oxygen double bonded to a sulfur, single bonded to a chlorines. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. And just to verify my formal charges, so this is going to be 2 lines and 4 dots. And now there is 1, 2, 3, 4 lines and 2 dots. And the chlorine is exactly the same. That works out to be 0. So this is going to be my structure. As for my hybridization, it's attached to 1, 2, 3 things and a lone pair. So that's sp3. And as for my shape, it's going to be over here, your trigonal pyramidal one, just like the ammonia. And that's it. So hopefully these examples will be of some use to you, and you are more experts now in the area of making Lewis structures.